All right. So yeah. So I think this is actually one of the better papers I've read over the past like 2 or 3 years, and it's not even a paper; it's a blog post. So it's very accessible, and if you're interested, then do read it because they explain it much better than I can. But it's also a very long blog post, so I try to pick the most important things, and it's not even all of it. So yeah, that's just a precursor to it. All right. So they kind of start off by saying, okay, well, with neural networks, we're trying to learn representations. And what are those? I mean, and they define it as their features of the input represented as directions in activation space. And I think that they just mean like if they're vectors, which is a different word for vector, of course. And then they ask the question like, okay, well, what do good representations look like? And so they start off using the linear representation hypothesis. And now you can see my notes, but they say like decomposability is important, which means that the network representations can be described in terms of independently understandable features. So that's like understandability. And then
sorry, what does understandability mean?
Like understandable to like humans.
Oh,
feature is like one component of a vector.
Yeah, yeah, and linearity. Which means, and the reason I think, so I'll get to it a little bit more, but the reason linearity, because I think that is like a little bit of like a weird statement maybe, because you think like, well, why would we go on linear? Like the point of neural network is to do non-linearities. But I think the point is that at the end, like if you think about the representation space of a classifier neural network, at the end you have this like linear layer that projects it to a class probability, right? And I think what they mean here is essentially that, like, once you have those features right before the classification, like the final layer, final linear layer, that's the type of features they're talking about. And because we train models that way, it also makes sense that they would be sort of linear related to things that we're interested in, which in classifier cases are classes.
Is it just, does it mean linear separability of the features?
No, they literally mean that the features are linearly related to what we think is interesting. Let me just grab my notes again. Yeah, I guess they just mean that they're vectors, like in a linear space. Essentially, that's the way to think about it. Like the features are embedded into a linear space.
So it does mean linear separability, like basically like in self-supervision, you take linear layer and if features are linear separable, then you have better classification. Like
I don't know if it's per se separability. That's like, the word I'm
like SVM, for example, you use kernel and then
no. They're not talking about classification specifically, by the way. I just use it as an example. They mean linear in the sense that you can decompose it into bases, like orthogonal bases, and then you can project the features onto those bases. Okay. And those bases sometimes mean something and sometimes don't, and that's what they define below, which is sometimes we have privileged bases, which in this case just means that the feature space itself has basis vectors that do what we want it to do, which is decompose into things that we understand. Like, for example, you know, hair, color, or something like that. Yeah, it is closely related. Actually, I'll get to the final part is about dynamics and also about sex. So,
cool. Yeah, I'm riveted now. Go.
Yeah. So that's what they say. Like privileged bases are essentially bases that have these properties, and then superposition. This is the annoying thing about sharing my screen. Superposition is that the linear representations can represent more features than dimensions. So in this sense, it means that neural networks essentially simulate larger networks, pushing features away from corresponding neurons. So it's like one neuron represents multiple features, and they have a lot of cool visualization to show what they mean by that. So I just wanted to introduce it. All right. So yeah, so their goal essentially is to demonstrate how superposition interacts with privileged bases. And that's like a very far goal. That's why the blog post is so long, but they'll go through it in like very simple steps essentially. And they also talk about how this is super important for interpretability, for example, but also for the work that Brad is doing in terms of the rank of the gradient and stuff like that. So yeah, it's
also kind of lines up with what Priyasat was doing.
Yeah, absolutely.
Although this is less about like sparsity per se.
Yeah, but the overlap part and the latest multitask.
Yeah, exactly. Yeah. Well, exactly, because for some tasks you have maybe features that are represented in superposition for different tasks.
Right.
Yeah, but when like he's working on right now doing it for multimodal.
Yeah, I'm working with it.
Oh, are you? I don't know what's going on in my own projects.
But do they relate it like with a disentanglement or like?
Yeah, so they talk about, for example, disentanglement is like they say that there's been like a lot of different ways of people describing the idea of getting good representations, but they take more of like I guess like they take more of a theoretical and empirical perspective and on a very small network. So it's like it's all in a very small contained analysis. But I think the results themselves are really interesting.
Yeah, maybe also like one question. So I think Joshua Benjamin, like in his 2015 paper, he talked about factors of variation. Maybe it's like the better way to put it.
Yeah, they actually like also talk about
finding contributes on sides of that.
Yeah, exactly. Yeah, that's actually this slide. Alex is one step ahead. So for example, like I think latent space with interpretable directions is partly, I think they quote like Benjamin's paper for this point. But so they have a few empirical observations that we had. For example, with word embeddings, if you have the embedding of king and you do minus male plus female, you get queen. That's like a famous paper in like the NLP space that you can find these types of like semantic relationships.
Word to vec.
What?
Word to vec.
Yeah, exactly.
But diffusion models also use the same thing. Like you're just walking in latent space and
right. Yeah. But I mean, they're just saying like we've seen that there is these types of like clearly this is like a privileged basis in their definition, right? Because like we now can like do arithmetic in a way that is understandable for us. There's been work on latent spaces with interpretable directions in both GANs, VAEs, and diffusion models. I have to go to my notes again.
Oh, so while you're doing that, the privileged spaces, so like it could work in any basis. The network could achieve its results in any basis, but some of the rotations or something will be interpretable to us. Is that what they mean?
So here, I'll just go to their.
I think simply put, it's just like clusters, like in Parsons window. You can just use cluster and like you have cluster for positive class, cluster for negative class, so you can find decision boundary. But why you can find decision boundary? Because you have space and you have distances, right?
No, but a basis.
But I don't
this
think
could be done in any basis.
Because in real life, we actually can't use bases. We're using like frames that are bounded in some sense. Because we're dealing with noise scenario. Like our data is noisy, we can't use just bases.
Well, this is their definition at least, which is that only some representations have privileged basis, which encourages features to align with basis directions.
So I don't understand this. Is privileged basis a base or because?
Well, okay, so I think it becomes clearer later, but their point is like if you want to represent features in this representation space, if they're orthogonal, if they can be represented orthogonally,
linear algebra.
That's like privileged because you can just represent a feature using the basis vector, which means that it's like no noise essentially. That's they talk about that later a little bit. Does it make sense? Like if you have to put
I'm confused. Is privileged basis different than an orthogonal basis?
Well, so they say, so a privileged basis is when an orthogonal basis corresponds to a feature in the representation space.
Okay.
Does that make sense? Like when we take a feature in let's say X.
So the feature is called privileged base?
No, in the representation space, there's a privileged basis. So if you think about X being high dimensional, like n dimensional, n look very much bigger than M, and we try to map it to M, which is a lower dimensional space. If any of the features Ni maps completely orthogonally onto M, that is a privileged basis.
The feature.
Yeah, exactly. Okay. Does that make sense? So this one feature takes up the whole orthogonal, it takes up this basis essentially, and there's no interference from other features. It's just like this feature has its own basis
Subspace.
vector. Yeah, its own basis vector in the subspace. Yeah.
Can we say, like, example, you have a queen, like king minus man plus female, and you get the queen, like in multiple. So this will be example of privilege basis.
Yeah, exactly. Yeah, exactly. They also talk about a few other empirical observations, like the university of neurons, which means that in different networks, you can find neurons that perform the exact same function. And polysemantic, I mean, I made a mistake here, but polysemantic neurons, which means that multiple things are represented in one neuron. So that's what they start with. And then they talk about linearity. So this is what they, let's get this lower. So yeah, this is their definition of linearity and why it makes sense that the representations are linear. And so here they talk about Bengio's writing, but I think they also refer to it, kind of refer to his paper. Right. So why is linearity important? Well, linear representations are the natural outputs of obvious algorithms a layer might implement. So because every single layer is essentially a linear mapping and then a nonlinearity, it would make sense that the representations themselves become linear, because then it's easier for the next layer to learn a relationship to them. Which is the second one. Like a typical neural network is a linear function followed by nonlinearity. If a feature in the previous layer is represented linearly, a neuron in the next layer can select it and have it consistently excite or inhibit that neuron. And statistical efficiency is also important.
When in 2011 I was talking to Yoshua Bengio that neuroimaging doesn't want to use the nonlinear models because everyone is used to ICA and other linear models for their interpretability and stuff like that. He's like, oh no, that's not the case. Deep learning is only slightly nonlinear.
Yeah.
So tell them it's okay. It's just like ICA, only slightly nonlinear.
Exactly.
So the statistical efficiency, they just means that the measure the quality of estimator, right? The bias is standard error. Okay.
Yeah, exactly. Yeah. So yeah, so here again they talk about the privilege basis. So these vectors, these two vectors to the left top and to the right top, they would be projections of features in a high dimensional space onto this 2D space. And you can see on the left, they do not align with the ortho basis, which means that if you project them onto the orthogonal bases, you would get part of y and part of x for the right vector and part of x and part of y for the
This
left vector.
story reminds me of ICA.
I know, yeah. I mean, I hope everyone had a linear algebra class. So you'll see that, like, but if it's a privilege basis, then you get vectors that correctly align with these orthogonal bases. And then there's no noise, you can think of it. Like if you think of y and x in this case as features in the representation space, then a feature in a representation space is affected, like for example, the right vector, right? On the left, the right vector will be partly in x and partly in y if you project it onto the bases. And that means that now this feature vector is kind of noisy with respect to the original feature, which is that vector itself now. Does that make sense?
So the left one is orthogonal too?
No. If you would project it onto the bases, you would get contributions from both basis vectors.
But this story does align with sparses.
Yeah, it is. Yeah.
But
does it make sense?
You said about Riasat's work. That it doesn't go.
Yeah, well, I mean, more like they're not like trying to enforce sparsity in the features themselves. I mean, that's more what I meant, or in the weights or something. This is specifically about the representation space.
Mm-hmm.
So this is like literally if you had a neural network, you know, convolutional neural network, and then right before the linear layer, we're talking about that space, for example.
Mm-hmm.
Does that make sense?
Yeah, I understand.
Does it make sense, Ashkan?
I mean, I don't understand what do they mean, because the rotation of the bases are the bases themselves, right?
Yeah, I was going to ask the same question. Like this looks like a basis to me, just in a different rotation. Like I don't see any.
I don't understand why one. I don't get it.
Okay, so you have to think about the fact that the basis for the features are learned by data, right?
So they don't have to learn to be orthogonal.
Yeah,
they don't have to be orthogonal. It's just an example on the slide. It's not just a rotation from one model to another.
Doesn't mean like
so it's not a basis, right?
It is a basis. Any set of linear independent vectors is a basis.
But so it's not guarantees that they're independent.
So I don't understand is that which basis do we consider? When we consider it privileged basis when features align with basis, right? Because we do not have a basis. We have several. It's not unique, right?
Right. So let me say it like this. If we have X, which is a high dimensional vector, and we have W that maps that vector to a lower dimensional space, and we don't change W, then some of the features may be unaligned with the basis vectors, which are like 0, 0, 0, 1, 0, 1.
No, but why that basis? Why are we considering that basis a good basis? This is what I don't understand. Why are we saying that, oh, if it matches those bases, it's privileged, but if it matches another basis, it's not privileged. It's because there is nothing to say that 0, 0, 1 is better than, I don't know, 0.2, 0.2, 0.2, right? Or something like that.
The point is obviously that we're trying to learn W. So like it should have learned that rotation if it was like the best way to represent the data.
Okay.
That doesn't really answer Ashkan's question though. I mean, Ashkan's right. Like you can have very, very many different bases that can generate a space, right? And they don't need to. And so it's confusing why one particular set of basis vectors would be privileged versus like an analogous set.
So think of it like this: if we have one dimension, right, which is just that's a feature that you extract, right? If you go from -3 to 3, it's more or less of that feature, essentially.
Maybe we could think about this in terms of the SVD would be helpful, right? So you learn a transformation W, right, is what you're saying. And so if you look at that, you look at the singular vectors, those are a unique basis.
Yeah, but it's a neural network, so you can't say that. The idea is like if you have 3 features, right? Like let's say color of hair, size of the nose, and like I don't know, like length of the mouth or something, right?
I guess, but then you're saying like that doesn't make sense in terms of the concept of like I'm not following that. If you can just say, oh, it's a neural network, and so we choose these 3 features and that's a basis, that doesn't make sense to me.
You don't choose them, it learns these bases, right?
It's like learning a parts-based representation. I can't help thinking about it in sparsity terms. This part.
Maybe it's like some compositionality. If it's purely basis, it's compositional. So, for example, you clearly know it's a dog, a cat, but in non-PLG basis, you might get a feature set and call a cat and a dog at the same time. So you have cat dog or dog cat. That's called.
Yeah, the parts-based.
Okay. I'm still not following the connection to the basis either, but I mean, I follow that logic, what you just said, but it doesn't sound like a basis to me, and I don't understand it in that sense.
No, well, but if think about the 3-dimensional vector, x1, x2, x3, and if you map size of the eye into x1, size of the nose into x2, and size of mouth into x3, versus you get the sort of separate bases, orthogonal bases for those 3 parts. But sure, you can map the same to combination of those, and then it's not
the point is that if it was an orthogonal basis, because we don't know what the rotation would be, right? So the point is like if it learns these orthogonal bases that we want to
that's what I said. Any orthogonal basis, if it matches any orthogonal basis, is privileged basis.
In this case, it's specifically if one of the features maps directly to this orthogonal basis. Like that means that feature is like in some way really important, and they'll talk about why in a second.
I think it is. It must be any orthogonal basis, Ashkan.
Yeah, because it doesn't make sense. Yeah, I mean, the left one is orthogonal to it, just the bases are different. So it just matches another two bases, which is the same privilege as the right one. There is nothing different between the two bases, right? It's not.
They're talking about specifically like 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1.
So the canonical basis then.
Yeah, exactly.
So, okay.
Yeah.
No, but I think there is no agreement. It's incorrect agreement because x1, x2, x3, they specify what the canonical basis is. There is no any orthogonal basis here. Any other, but that aligns with x1, x2, x3 will not be sparse. The one on the left represented in three x1, x2, x3 will be smoothed out into all of them. So and the one on the right will not be smoothed out.
Because the vectors that you see are two different features. So if the feature that is on the right represented by the y-axis appears and the other doesn't, you get a sparse feature space. If that makes sense.
I think we are on agreement now because the canonical basis is one basis. That is, there is a unique set of basis vectors that are the canonical basis, and so if they map onto that particular set of basis vectors, that makes complete sense. That it's unique.
So that's the point. Yeah.
Okay.
Okay. Right. So then this is their hypothesis. So, well, first of all, they talk about polysemanticity, which is that we'd expect to observe if features were not aligned with the neuron despite incentives to align with the privileged basis. And their own superposition hypothesis that if you have more features than the number of dimensions that you map them into, that you get this polysemanticity where they can't align with these canonical bases.
To me, like first case, it looks like hallucination, like in neural networks. Second case is like when you have, for example, color, shape, and something else, and network chooses like the simplest features, 1 out of 3 features.
Yeah, so that's that's what they're going towards. Yeah. So they say that this is important because you have almost orthogonal vectors. You have exponential n for high dimensional spaces n, and you only have n orthogonal ones. That's what they say. And this also makes sense because in compressed sensing, a lower dimensional mapping cannot fully reconstruct unless we know the lower dimensional space is sparse. So here comes back the sparsity part of their argument.
I think it's like manifold hypothesis that features layer like the large dimensional manifold.
Yeah, but they specifically talk about sparsity of the features because then you like that's like you'll see it with the results in correlated and intercorrelated stuff. But that's how you can represent it the most efficiently.
Are these, sorry, is this almost orthogonality because of the numerical error and the and so it's like it's nearly zero, you know, if you take the dot product, or what do they mean by that? And it's just like within some precision.
Yeah, so this is their explanation. So
I see. Yeah, exactly. So it's machine epsilon orthogonal.
Yeah, exactly. Yeah.
Interesting. Okay, that makes sense.
Okay. And so then they start talking about essentially interference between features. So each of these black vectors is a feature that is mapped onto this lower dimensional space. And if you have, you know, yeah, so sorry, the yellow one is a feature mapped onto this lower dimensional space. And if only one feature is active, we get, you get interference in this case. But if the features aren't as sparse as a superposition is expecting, then you can represent multiple features can additively interfere. Yeah, if anyone has.
I just think they're using this cosine similarity, like contrastive perspective, like that you have sphere and you have direction in sphere. And it's like inside the 0-1 sphere, but like have like a lot of directions.
Mm-hmm. I mean, I think it is related to a lot of different ways of thinking about like learning features for sure. Right. Okay. So they say that under their hypothesis, essentially what smaller networks are doing is simulating larger networks. It's a noisy simulation of larger neural networks, essentially is what they're saying. And the way it works is that these idealized neurons for like the really big disentangled model are mapped onto the actual neural network that we have as almost orthogonal vectors over the neurons. So it's a low dimensional projection. And I understand if people are like a little confused, I think it gets more clear later on actually. Like I was in the beginning, I was also like, oh, what's going on? But I think it helps to think about it in these terms.
Yeah, right. This part I'm following.
Okay, cool. Yeah. Well, that's good. Yeah, please let me know if anyone doesn't follow because we can like understand it together, I think better. Okay, so I already mentioned these things, but there's a few things that are important about features, that they're decomposable, that they have linearity. You have superposition versus non-superposition, and non-superposition is essentially like a little bit more, is less noisy because you don't have interference from other features, and they're basis aligned. So essentially what they're saying is the latter two occur sometimes, and they're going to show that in the next experiments, and the first two are widespread, like they're kind of commonly known. So yeah, I think this is not super important. What they do is they create synthetic data where they, essentially the arguments for how they create it is that you have a lot of feature sparsity in the real world. So they have a sparsity parameter S that they use to generate the features. Oftentimes in the real world, you have more potential features that you can learn than neurons. So not per se the number of features in the raw data, but just the more potential number of features you could learn, because combinations of the original data can lead to features that you can use to classify or whatever. And features vary in importance. So their model is, they compare a linear model to a ReLU output model, and this is pretty important. So we have X, which is high dimensional. In fact, it's, let me think, it's n dimensional. And W is m by n. So we map X to a lower dimensional space H, and then we try to recover W again to map it back to a larger space. And that's what they're saying here. So X, is that called apostrophe, is the reconstruction. And that's also how they train it. So it's essentially an autoencoder with W in real matrix n by n. And then the loss they have is I here is the importance of each of the features. So the features in this case are talked about in X, and we take the mean square, or we take the sum square error. Okay, before we get to the real results, the first results, because there's like 10 of them, this is how they visualize the results. So it's easier to visualize WTW, which is like the unnormalized covariance matrix of how the features map to the space. So let me just go back really quickly. So how you can think of it is like Xi is a feature, right? And then the column vector Wi is how it maps that feature to H, to a dimension in H, if that makes sense.
Yep.
Okay, cool. So yeah, we want to look at W transpose W because it gives us the covariance of how these features are mapped. Yeah, so this is the way they visualize it. And yeah, so the way they think about it is like if a feature is represented in superposition, that's determined by the norm of this column vector Wi. And we can calculate the projection of all other features, Wj, which is also a column vector, onto Wi, where if it's 0, it's orthogonal to each other, the projection. And if it's larger than 1, there's some group of features which can activate Wi as strongly as feature I itself. So that means that they're in superposition. So this is for the, What?
Sorry, I have a question. It might be dumb. So I don't, from signal processing superposition, the principal superposition only applies to linear system, right? So are they trying to apply to nonlinear systems here?
Yes.
Is it approximation, or are they trying to do the principle in a exact mathematical?
They also use an exact mathematical way, but they can, because Sachs has done a lot of work on the dynamics of ReLU networks, they can use that work, if that makes sense. So they only have one nonlinearity, by the way. I mean, it's a very simple neural network.
But I thought that it's proven that superposition actually cannot be exact for nonlinear system.
So it is an approximation, Ashkan.
It is an approximation.
Pretty sure.
Okay.
Yeah. I mean, so the way what they say is like, I mean, they look at like how superposition like changes during training using Sachs's stuff, but they approximate it using this measure that they say kind of indicates whether there has been superposition or not.
Yeah. So even Sachs's results were that the ReLU dynamics could be approximated by linear dynamics, right?
Yeah.
So they're not exact, but you can get close.
Yeah. I shouldn't say like exact. I shouldn't have said like exact, but so this is kind of the way they think about whether something has a superposition. But yeah, it's not.
Okay.
It's an approximation.
Got it.
Does it look like they use like linear encoder in some sense? Like,
Yeah. So they have a linear autoencoder and they have a autoencoder with the ReLU on it. Okay. So this is how they visualize the results. It's really simple.
Linear autoencoder is a PCA, by the way.
Yeah,
it's an
Exact PCA.
Yeah. So this measures, so black means there's zero superposition, and then 1 means there's a lot of superposition. Yeah, and then this is the norm. So how large, so the color is if it's in superposition, and the norm is how important that feature is. And these are, yeah, it takes some time to, these are the results. So
it feels like they're just correlating features of the like you take a layer, linear layer, and then you take the W and you compare correlation between each other.
Yeah,
so
this is.
They just find the correlated features.
now the correlated projection.
Well, do you remember, Alex, when I was doing this FNC-like interpretation of neural networks? We and Sergey, you might remember too. We found a very similar result, at least, initially. You get these, set of, in the identity, and then these kind of little modules that, show correspondence a very similar way. I don't know if we were looking at ReLU models though, but we were doing, basically this exact same thing.
Like there is a work called similarity representation. Like it's a Simon Cornitz, this work, SKA, they're using SKA. But it's basically the same thing. Like you just basically trying to find features within the layers that relate with each other.
No, because this is the projection itself. This is the correlation of the projection, not of the features. Because W is a projection matrix. So they're doing the correlation between the projections.
You relating the features, right? The neurons itself.
Yeah, that's why I said it was like what we did with the FNC stuff, or what I did with the FNC stuff back at MRN. We were just looking at the correlation of the neurons.
Right.
Yeah.
Okay. And so, yeah. So what they find essentially is that in normal linear models, you don't, at least in this case, they don't get any superposition. But when they increase the sparsity of the features, they get, for the ReLU model, they get a lot of superposition. And the reason behind that is like, if two features do not happen at the same time, then we may as well just represent them in superposition because they're not going to interfere that much with each other anyways. And it's more efficient that way.
That's interesting. So sparser results are obtained by denser transformation. Sparser features. So if the input features, the input features X, we can represent more of them if they're sparse because we can put them in superposition with each other. And since they're not going to interfere with each other. Input is sparse.
Yeah, input is sparse.
Not the latent space.
Not the latent space. Yeah,
Oh,
if the input is more sparse, if features do not happen together with each other more often, we can represent more of them, but in superposition, which I think intuitively makes sense. So if there's no sparsity, if it's completely dense, we get the exact same thing as a linear model. But as we increase the sparsity of the features, we can represent these features in our lower dimensional space in superposition, which is the yellow thing. So it goes from not sparse to sparse.
But superposition or representation is dense now.
Exactly. Yeah.
It becomes dense.
Yeah. Although the activations, because the input features are sparse, are also often going to be pretty sparse.
Oh yeah. So because it's basically a selection operator,
exactly.
Just one of the columns.
Yeah, exactly. And so they also show the same thing for more features and hidden dimensions. Yeah, I hope everyone is following this because it's going to get like, it's going to go a little bit more.
I think I'm on board still.
Cool. Okay, so they say, well, why? And they use Sachs's work to essentially decouple the loss function into a feature benefit and an interference function, where if you want to minimize the feature benefit, you can just add more features. So you can try to represent more of the features in X in your lower dimensional space, but that increases the interference, which will become higher. So there's this constant battle between trying to minimize interference between features that you're representing and representing more features, because that way you capture more of the data.
Oh man, Kishvi's, this is also information bottleneck stuff related. It all comes together.
I know. Well, so that's what they're saying. So more features get a better loss, but then there's interference when you try to represent too many features.
But there is also another perspective that, like, they didn't check for region values, but there is a research from Baker, I don't remember his name, but he had this presentation on ICLM that he was talking that you have like a lot of region values like in lower values, but like if you have them more, like then you represent more features. And so basically if they check the region values by adding features, they will see that a lot of region values should be still low, then interference should be like, it makes like interference lower if you have a lot of small region values.
Yeah,
like,
yeah, that makes sense.
We probably can try that, and that should kind of connect those.
Right. So I hope this makes sense from the perspective of the previous figure too. If we have sparser features, by definition, there's going to be less interference because features themselves interfere with each other less. So what we can do is we can represent more of them, because this, we can now decrease this, right, by having more features. And this is not going to increase as much because the features themselves are sparse. So we don't have to worry too much about the interference happening. All right. Yeah, this is the math they do to like to go from Sachs to their result.
Is the noise sparse too, or
what did you say? Sorry.
Is the noise sparse too?
I don't think so.
I don't think they have a lot of noise added to their data, to be honest.
Okay.
They're just talking about like if you just think of the features as 0, 1, it's just more like, okay, well, feature I is 1, then feature J is not 1. Like essentially that's the.
Oh, okay. So it is estimation error, not the interference that they call it is because of the estimation, not because of noise, right? Then. Yeah,
exactly. It's because two features are both active, and if you map them to the same, if they're both in superposition, they're going to interfere with each other, right? Like the value of your feature in the lower dimensional space is going to be part of feature 1 and part of feature 2 instead of just feature 1 or feature 2.
Okay.
Okay, so far, there's a summary, which is that there's a few things that a model can do. It can just simply not learn certain features, which is what happens when it's very dense, which we saw in the first case. Features may be learned and represented in superposition, which happens more and more as features get sparser. And the model may represent a feature with a dedicated dimension, which means that either the feature is super important, so we don't want any interference from other features, or this happens, in the case of the first one, which is this one. These features clearly are super important here. When it's super dense, we need to have those features represented for some reason. All right. now we're going to go another step further. So we can look at this as a phase change. And what they do is here is they have X is now 2D. So we have two features and we have one subspace. So it's a single value. And as we increase the relative feature importance of feature, so we have two features, right? Feature 1 and feature 2. If we increase the importance of feature 2, that's the x-axis, and then the density or the sparsity of the feature is on the y-axis. So we're only changing one feature. What you can see is that there's some sort of phase change where either if it's really dense and not very important, it'll just not be represented because the other feature is more important. And when the feature gets more important than feature 1, feature 2 gets more important than feature 1, it gets its own dedicated dimension, which means that the other feature is not represented anymore.
Yeah,
and the rest of the
cool.
time,
sorry, this is
Yeah, exactly. I'm not sure why they're doing this. What are they trying?
You're not sure why they're doing this, so it's basically they're able to show that man, the representation is you're requiring not that you're requiring, but I don't know. I need to think about this more, but this is I think really cool.
The rest of the time, when it's sparse, so when it's below 0.8, it seems like here, they're actually they're actually in superposition, right? That's like exactly at the phase change, the bifurcation essentially. And the cool thing is that they use Sachs's theory to also show that this works in theoretical prediction. And the way you should think about it is like, it's very easy in this example. So if we have two features, you should imagine X is a two-dimensional vector. Either it represents the first feature, which is this one, the gray one at the top, or when feature 2 gets more important than feature 1, it gets its own dimension and it's not representing feature 1 because it maps to 0, or they're going to be in superposition, but in an antipodal way because they're independent. So they're going to be opposite of each other in the neuron. So the way you can think about that is that from 0 to 1 would be feature 1 in the latent space, and from 0 to -1 would be feature 2 in the latent space because they're in superposition antipodally. All right. Cool. So conclusion is that sparsity is necessary for superposition to occur because otherwise it's not going to represent, otherwise it's just going to represent either one of the features. And there's a first order phase change in the theoretical model and a crossover between functions causing a discontinuity in the derivative of the optimal loss, which also, again, refers back to Sachs's work. Okay, now what happens if we have three features? So we have X is now three-dimensional and M is two-dimensional. So the lower space is two-dimensional. Now we get four essentially important results, which is, again, that the third feature is not represented, which you can see in this matrix because it maps to 0. That there's a superposition between, in this case, feature 2 and feature 3 because they're antipodally related, 1 and -1. That there's a dedicated dimension and another feature is not represented, which is when like feature 3 is super important, which you can see here in the top right. Or when there's a dedicated dimension for feature 3 and the other two are in superposition. And this is kind of their way of saying, well, you can imagine this in like very large dimensions, essentially.
This is so cool. Sergey, we have to publish our theoretical paper because this is like so closely related, right? We have, a hugely higher dimensional feature space, but we're restricted by the dimensionality of the model or of our output space. And this is just describing exactly how those features get collapsed onto this lower dimensional representation. With auto differentiation, we get a totally different perspective. So we have still stuff to talk about, but people are really snipping around what we've been already kind of finding.
I don't want to comment, Brad.
Yeah. No, I mean, I'm mad at myself, right?
Yeah, exactly.
Okay. Well, but we have to go even further, and now it gets really pretty crazy. So you can look at the geometry of the superpositions. This is when Noah wakes up.
No, I don't. Nothing is helpful there.
You can see here on the x-axis is how sparse the features are. And on the y-axis, it's the number of dimensions we have per embedded feature. And the important thing here is that it's kind of sticky is what they call it, when we have exactly one dimension for each feature. And it's sticky when we have half a dimension per feature. So when it's half a dimension per feature, because it doesn't, like, you can see this kind of like, it just, like it doesn't change much.
There's a plateau.
It doesn't change much, yeah. As it gets sparser, we still keep a half a dimension per feature. Does it make sense? Like we still represent each feature in half a dimension.
So there is some kind of a stationary region or something.
Yeah, exactly.
Changes, so.
Yeah, that's a better word than sticky, but.
No, I just couldn't.
And so the way they calculate it is like this. So they look at the projection of other the projection of the projection onto other features. It's not super important, but this is the formula. And now we get to the pretty crazy part. So they actually find that there's different geometries in this like plot. So it's still the same plot as I just showed you with the sticky region here in the middle, but they actually show that like initially we have a dedicated dimension, which means that it's just a point essentially. Then we go to a tetrahedron, then a triangle, and then a digon antipodal pair. And that's because it's half. So we have one feature on one end of the podal and one feature on the other end of the podal. And so antipodal just means they're diametrically opposed. So they're like exactly in opposite to each other. That stays for a pretty long time as sparsity increases, but then we get to a pentagon, a square antiprism, and at some point it's going to be features not learned, which is 0 dimension. And the way you can think of this is like 1/1, and then 3/4, 2/3, 1/2, 2/5, 3/8, etc., until it's 0, which means that it's not represented.
Yeah, this is interesting, but I think this geometric nicety is probably an artifact of their model. Like I'm a little suspicious that this wouldn't show up in other models.
Well, it's actually very similar to PCA, which is what they talk about next.
Interesting.
So
okay.
The reason actually they also do this is because they show that they're, what was it? So this is very much related to, here, let's take it. The Thomson problem in electricity, where they see the exact same shapes happening. I don't know if that makes you more comfortable or not with the
like the Coulomb forces.
Yeah, exactly. Where do they talk about the Thomson? They talk about it a lot, the Thomson problem. So yeah, this is the feature benefit and interference that I just showed you. The mathematical formula for like what the loss is pulling between is like very similar to the Thomson problem in chemistry. And they actually find the same type of shapes as you would find with the Thomson problem as well.
Right, but I still think, so I'm not familiar with this Thomson problem, but they're like choosing a very restricted model. And I don't think, yeah, I don't think that when you expand the model beyond this, it would show the same transitions.
No, sure.
It also has to do with the symmetries, like Thomson problem. Yeah,
it's about the symmetries between the superpositions.
Yeah, like I think if you change the symmetry, like parameter tying or anything, like, well, we know it changes the situation. Okay.
Yeah.
So what they show is that all of these shapes are essentially combinations of polytopes, which I've just shown you a 2-dimensional and a 3-dimensional polytope, and specifically related to the Tegum product, which is when you embed 2 polytopes in an orthogonal subspace. So when you have a bipyramid, which is this one, and a antipodal shape, and you add them together into orthogonal subspaces, you get a triangular bipyramid. And then when you have a pentagon and an antipode, you get a pentagonal bipyramid. And when you have multiple antipodes, you get an octahedron.
But isn't the come like just that we have 3 and it's like will be optimal packing?
Yeah, exactly. That's yeah, exactly. And that's also why it's related to the Thomson problem, because then you're trying to pack multiple things into a sphere too.
But with the problem of Thomson, like, does it relate to the like energy-based models?
Yeah.
So we also have the Boltzmann machines here.
Well, I mean, they're just talking about a very simple network, not per se about training the Boltzmann machines, but could be related.
But Dr. Please, is like Boltzmann machine related to Thomson problem?
I can't say, I don't know. That's the first time I hear the connection. So I don't.
I think it's worth looking into.
Because contrastive learning could also like in a sphere and using this Boltzmann kind of
Could be.
You could enforce this geometry.
Repellent forces and things like that.
You can enforce this geometry probably in self-supervised learning.
But I know now why Noah is attracted to the geometries, because now when I'm seeing it, I'm also like, ooh, computer science, finally.
Yeah.
Like the real
to get a better idea of what
like
polytopes are, is that if you want to do 3 features in a 2 superposition, that corresponds to a triangle. So this is a 2D space of 3 features, you would get a triangle. And if there are 3 equally important features, you get an equilateral triangle. So that's kind of the way you should think about it.
But this is again symmetry is at play.
Is it provably equilateral, or is it an estimation of it? Is it kind of equilateral?
I think it's, well, I think generally they have approximations.
Okay.
Because it's a neural network, so you have
Yeah.
to kind of, but yeah. I mean, they can't prove anything because they have a nonlinearity, so it becomes very hard to like prove. But I think if their idea is essentially, it does like converge to this shape.
But maybe that just has more to do with separability, right? That the model is trying to separate the features as much as possible, and that separability is most similar to something like a triangle.
Right. Well, specifically, if you think about this superposition of sparse features, you can represent it like this very efficiently with the least amount of inference or something, interference between the features.
Interference.
Yeah, that's how they called it when they kind of like are both, and then you get like a.
Yeah, because it's related to orthogonality. Maybe.
Yeah, exactly.
So
yeah.
that's kind of the point. Is that it's just the most orthogonal, and so
yeah, exactly.
The shapes that are most orthogonal.
Yes,
that's what it looks
exactly.
like.
Yeah,
exactly.
My reading of this currently is and this is maybe a little bit cynical, is that it just feels like this is a geometric imposition of why people also how people detect the golden ratio and the growth of plants and shit like that. Like it's, oh yeah, of course it grows like this because it's just biologically efficient, right? It's like there's no meaning beyond that.
No, yeah, I mean, it kind of is, but I think still it's an impressive result. I think it's interesting to think about. I don't think they've like proved it very rigorously, or they haven't shown it in bigger networks, but I still think it's interesting to think about it like this. It's a new direction, I would say, to think about these types of things.
Cool.
Now after this word spread, I'd say, yeah, let's publish it as quick as
yeah, it's ready. We need to get someone to look at it, and we need to just get it out.
And so now they're going to do it a more intense analysis, which is with non-uniform superposition. So now the features are varying in importance or sparsity, and they have correlated and anti-correlated features. Yeah, so this is their experiment. Like if you have 4 features and you vary the sparsity, you get like a pentagon solution essentially. Yeah, that's what happens. When the sparsity of the varied point falls below a certain critical threshold, then it'll become 2 digons. So when the feature is like super sparse, it is just represented, like you don't have to represent it anymore. That's, I think, the point.
So what is the middle point? You said 4 features. What is the middle point?
So we have 5 features, and they're
saying 5
features.
Features. Okay.
Yeah, sorry. The middle point. So we represent all 5 in a pentagon, unless this middle feature gets like a sparsity lower than 2.5 times less than the others, and then we can just represent everything as a 2 digon. So this shape. Okay, and what they show actually is that stochastic gradient descent can't really find these things oftentimes, and they have to use a theoretical model to find the best loss, which is to keep using this pentagon essentially.
Yeah, I was just thinking about multi-body problem. it has to move the things around.
Right. Yeah, it has. Yeah, that's why I think it is interesting, the geometry. Like it may not be provable, but I do think there is that makes some intuitive sense, because if you want to fit it, like Alex also said, if you want to fit it into a sphere, there's like only, you have only certain types of shapes.
Because Yannick talks about a lot this volume optimization.
Yeah.
So I think the pentagon will be best configuration.
Yeah, exactly. With the least correlated between the right. Okay, so then their conclusion is they jump between uniform superpositions for when you vary the sparsity, and the gradient descent is issue with these jumps. Then they look at correlated versus anti-correlated features, which is bundles of co-occurring features and bundles of like anti-correlated features where only one feature can be active at a time. And it looks like this. So this is, yeah, so I think, yeah. So models prefer to represent the correlated features in orthogonal dimensions. So that's these ones, red. And this is blue is also correlated. And if they're anti-correlated, it's the bottom one, which is that they're dipoles or anti-pole or something, what they call whatever. Well, they're diametrically opposed to each other. So
well, orthogonal, right? The bottom ones are orthogonal and the correlated ones.
No, sorry. So blue, the blue points are two features, but they're correlated with each other in the top, and they're anti-correlated in the bottom. So two features that are anti-correlated are like represented in the opposite direction.
So there are a total 4 features in the slide.
Yeah, exactly. There's 4 features. Yeah, exactly. And they also show that, what's the green again? Yeah, this is when you have like 6 features and only, and you have less subspace dimensions than the number of features. You get again this sort of like superposition shape. This is all empirical results, by the way. Like you can see that the lines are a little squiggly. That's because it's like real empirical results. And they also find that
these are only holds for M2, right? The second the dimension 2.
Yeah, exactly. In dimension 2. So you get the superposition because
so in dimension 3, they won't be opposite each other, right? They won't be orthogonal.
In a different configuration, probably, right? Okay. It'll be more similar to this one again, because now you have an extra basis.
That so they can be ortho. Yeah, okay.
Yeah, so you can represent green on that new basis, but if you don't have it, you have to represent them in superposition to each other, like this.
Okay.
That's their point. So yeah, I'll skip over this, but this is like locally orthogonal basis. You can see that if you have a correlated feature set, they have an orthogonal basis with each other, and they have like this sort of correlated, the 2 feature sets have some like interference with each other. So they show that, they show that there's a relation to PCA, which is that if there are 2 correlated features, A and B, but you only have capacity to represent one, you're going to represent its principal component, which is a sparse variable, and has more impact on the loss than either of them individually. And then they show here the PCA-like versus non-PCA-like results, that as you increase the correlation, increase the sparsity, I think, you get less results like PCA, essentially. They also relate back to dynamics. I'm going to go over this pretty quickly because it's just more a teaser. Yeah, they also show these like changes in the loss.
Yeah, exactly. Next door, crosstalk.
And then they also show that over time you can see kind of these shapes forming during training, and that's some of the bumps in the loss function is when it expands its shape into a more complex polytope.
That's interesting.
So Brad.
Telling you.
And then Alan, no one just left, but they also show a lot of relations to interpretability research, where they say that if you have a privileged basis, it makes this projection W more directly interpretable, because this is a linear stage. But if you have a really, you get these like you get this important substructure here in the matrix of W, which you can more directly interpret.
It's actually not new. It's a linear problem. So
right. No. I agree that
you can use a while ago, like 2016.
Yeah, you made me interested in reading that blog post.
So that's my final conclusion. I tried to read it this morning in an hour, but if you're interested, please just read the whole blog post because it's very hard. I try my best, but it's very, I mean, there's even more. They compared to adversarial examples, they have double descent.
We should do something like that as well, like those posts.
Yeah.
Yeah, that's because I was thinking like if this hasn't been accepted, but this is still awesome, we should just continue. We should just do that. Like it's so frustrating.
Well, I feel like in the eyes of a lot of people, this is accepted because I've seen like so many people on Twitter like use this already in their work.
It's so
because
silly.
You can cite this actually because it's their own. Anthropic AI doesn't really publish papers; they just post it on their blog, and then people just cite from their blog.
Yeah, academia is a joke.
But I was wondering, can we do like some like geometry in sense, like you can find attractor points like in fMRI and use this like as guidance for our models?
I guess. Yeah, let's stop here though and
this
move
is
into the
interesting stuff.
But thank you. Yeah, thanks. It's been on the radars for a while, right?
Yeah, I sent it like 6 months ago.
Finally, yeah, thank you.